Hi, everyone. I'm Dan, and today I'd like to talk about Faraday's experiments on electrostatics, Gauss's law, and divergence. This is my second video in what will hopefully be a series on videos in electrical engineering, specifically electromagnetics, possibly EMC, EMI, maybe RF, microwave, circuits, antennas, etc., etc. So we're going to dive right in. So going back to my last video, just a brief overview of my last video, we talked about Faraday's 1837 experiment on electrostatics, where he had two concentric spheres. He charged up the inner sphere to a known positive charge, and then he clamped another sphere concentric around it, not touching it, with a dielectric material in between them. The outer sphere was momentarily discharged by connecting it to ground, and the large hemispheres were then separated carefully with insulating material so that it wouldn't disturb the charge induced on it, and measured, and it was found to be equal in magnitude and opposite in sign to the charge on the inner sphere. This was a big deal, as we discussed last time. From this, Faraday concluded that there was some kind of displacement flux or lines of force, that the charge on the inner sphere was emanating toward the outer sphere, and somehow this displacement flux induced discharge on the outer sphere. And this was true regardless of what the material was between the spheres, what the dielectric material was in between the spheres. And then in 1843, he did a similar experiment called it's known now as the ice pail experiment, where he had this metal ice pail, and he had it put on like a wooden stool, insulating stool here, and he had it connected to this electrometer over here with these metallic leaves, and as he put this charged sphere into the ice bucket without touching it, he observed a deflection in these metallic leaves, again indicating that the charged sphere produces an electric field. The electric field is then incident on the interior of the ice pail, which induces an opposite charge on the interior of the ice pail. That induces an opposite charge on the outside of the ice pail, and that causes this deflection here in the leaves of the electroscope. So as I mentioned, that from these experiments, Faraday concluded that it's some kind of displacement between the inner and outer spheres that was independent of the dielectric material. Today, we are familiar with the concept of electric fields and electric flux, but that idea was not in the mainstream at the time. This idea of fields or line of force were very new to the scientific community in Faraday's time. I just recently read a great biography on the electric life of Michael Faraday by Alan Hirschfeld. And one of the things that he said in this biography, he mentioned, for 2 years, Faraday had assembled his array of evidence against electrical fluids and the action at a distance theory. In this effort, he was almost alone among scientists. In whatever way I view it, he told his colleagues, with great suspicion of the influence and favorite notions over myself, I cannot perceive how the ordinary theory applied to explain induction can be a correct representation of that great natural principle of electrical action. So at the time, there was this fluid theory of electricity, that electricity basically flows in fluids. There was a two-fluid theory, a positive fluid and a negative fluid. Later, that gave way to a one-fluid theory. But neither of the fluid theories really took a proper account for all electric phenomena, particularly when it came to the idea of fields or lines of force, and also the relationship between magnetic and electric fields, and how time varying magnetic fields induce an electric field and vice versa. So that really started to be developed by Faraday, and then was kind of crystallized mathematically by Maxwell. Incidentally, Faraday had virtually no training in mathematics, which really just shows how great of an experimental physicist he was. He was able to perform all kinds of experiments and make all kinds of scientific discoveries just describing the effects using the English language, and he didn't have the mathematical education or capability to express these ideas mathematically, and yet they were true, and later Maxwell and others were able to express the ideas that he articulated in a mathematical form. So speaking of mathematics, this idea of charged particles producing fields and that those fields producing inducing charges on other metallic objects can be expressed in Gauss's law. And Gauss's law in words basically says that the total charge enclosed in the volume bound by a closed surface is equal to the total electric flux emanating out of that surface. And by emanating here, we don't mean that there's some kind of motion going on. What we're doing is we're visualizing lines of flux oriented outward all over the Gaussian surface. So here we have just like an arbitrary closed surface. It's continuous, it's closed, and the total charge enclosed in this volume, total charge enclosed by this closed surface, is equal to the total electric flux emanating out of that surface. So if you take like this little differential window area here, and you look at the electric flux density at this area divided by this differential surface area, or I should say multiplied by this differential surface area, and you integrate that over the entire surface, then that would be equal to the total charge enclosed by the surface. The electric flux, the total electric flux will be equal to the total charge enclosed. And they're equal in units as well. You have the units for charge is coulombs, and the units for electric flux is coulombs. So expressing this mathematically, again, if we consider this differential electric flux emanating out of a differential window in the surface, we can say that the differential flux d phi equals the electric flux density, the normal part of the electric flux density at that point. So you have the electric flux density dot product with ds. ds is this differential surface area, and that is a vector. And so you have a dot product here, and you get this differential flux. You integrate that over the whole surface, and you get the total electric flux that's enclosed by the surface that's equal to the total flux, total electric flux. The total charge enclosed is found by integrating the volume charge density over the entire volume. So the total enclosed charge is going to be the volume integral, which is a triple integral of the electric charge density throughout the volume. So when you bring these concepts together, you have the total electric flux density integrated over the entire closed surface of the surface is equal to the volume integral of the total charge density integrated over or throughout the entire volume. This should make some intuitive sense, but this is expressed mathematically. This is something that Faraday was never able to do. He was never able to express his ideas mathematically, but this is what he confirmed by experiment in his concentric spheres experiment, that the total enclosed electric charge is equal to the total electric flux that he observed, because this electric flux induced the negative charge on the outer metal that was surrounding the space. So going from Gauss' law to Coulombs' law, Coulombs' law actually was articulated well before Faraday came around. This is Coulombs' law right here. It's saying that the electric field induced by a charge is equal to that charge divided by 4 pi epsilon a squared in the same direction, in a particular direction. So you have a charge, and as you go in the radial direction, then around the charge there's established an electric field that's equal to the charge divided by 4 pi epsilon a squared, where a is the distance from the charge and epsilon is the permittivity of the space. That was Coulomb's experimental observation, but we're going to basically derive that from Gauss's law. So going back up here, if we consider a simple point charge at the origin in a spherical Gaussian surface, a closed surface with a radius a from the origin, as we have over here, then as we integrate using Gauss's law, then the electric flux density times a squared sine of theta d theta d phi, integrating from theta equals 0 to pi radians, and from phi equals 0 to 2 pi radians to cover the whole surface of the sphere. We should find that we get the charge enclosed. So as we do this, it's a fairly straightforward integral given the symmetry of the problem. We find that the D field, the electric flux density, is Q enclosed over 4 pi a squared. Very familiar because when you multiply this, or this is the electric field times epsilon, the permittivity of the space. And so when we simply divide by the permittivity of space, we get the E field, and this is Coulomb's law. So let's talk about divergence. What happens when the volume under consideration becomes very, very small? In other words, when the volume under consideration is the differential volume. By Gauss's law, the total charge in the differential volume is equal to the closed surface integral of the electric flux density over the closed surface. Equivalently, the total flux emanating out of this differential volume divided by the differential volume is equal to the volume charge density. So the divergence of a vector flux density is defined as the outflow of flux from a small closed surface per unit volume as the volume shrinks to 0. So Gauss's law says the divergence of the electric flux density is the electric charge density. Divergence is the key thing here. Divergence, the definition of divergence is the limit as the differential volume shrinks to 0 of this closed surface integral of the electric flux density divided by the differential volume. And so this closed surface integral of the electric flux density is basically the flux emanating out of that little volume, out of that surface around that little volume divided by the volume. Key concept here is divergence is flux divided by volume as that volume shrinks to 0. And so what we get is a density. And by Gauss's law, we see that that density is it's flux per unit volume, but that would turn out to be the electric charge density by Gauss's law. So to visualize divergence, this is an important thing. We need to be able to visualize divergence. Sometimes people have a little bit of trouble with this. Divergence is a scalar, but it's a dot product. So here's a vector field, and you can see the vector field. It's radiating. Well, radiating. It's emanating outward. Okay, And if you just picture like a sphere somewhere over here in the center, then the divergence of the flux would be the total outward flux emanating out of the volume as that volume shrinks to zero. So that's kind of what we're thinking about when we think about divergence. By Coulombs Law and Gauss Law, we know that a positive charged particle establishes electric flux oriented in the radial outward direction. If that charge was held in place and if a positive test charge was forced near it and then released, the test charge would accelerate outward along these lines of flux. The divergence of the vector field at a location in space is a scalar that tells us the density of the outward oriented flux at that point. So when you see if you're visualizing a flux or an electric field, electric flux density, if you're visualizing a vector field, you should be able to discern or have an idea of what the divergence is at any given point. Just think about the net outward flux from any given point, and that's the divergence. And so if there's flux coming in and flux going out, and if they're equal, then the divergence would be zero. And that you can think of a river. In a river, the fluid flow, the divergence would be zero in most places in the river because the fluid coming in equals the fluid going out. And so the divergence at any particular area is zero. For the divergence to be positive or negative, if the divergence is positive, you can think of it as a source. If there's like a spring and there's just water flowing outward all the time, then you would have, that would be a positive divergence. If you have a sink of some kind and you have just like water flowing inward, then as it's flowing inward, if it's got no place to go, then the density gets greater and greater and greater. That has a negative divergence, or we can say it's a convergence. So we have divergence, negative divergence, which is convergence. So in Cartesian or rectangular coordinates, this is what it turns out to be. We can use this div for divergence of an electric flux density or any vector field, but we can use this del operator. This is the divergence operation, del dot the vector field. And the way to think about this is, so here's our little differential volume, and we have like dx, dy, dz in Cartesian coordinates. So if we look at the divergence, if we look at the electric flux emanating in the x direction or in the negative x direction, the x direction here, think about the electric flux emanating out, and then the electric flux emanating out the other way, then the electric flux, the difference, or the sum of the two would be equal to the net electric flux radiating outward in the x direction. And you can do the same thing with y and z. And so what the divergence is in Cartesian coordinates is simply the partial derivative of the component of the electric flux in the x direction with respect to x plus the partial derivative of the electric flux density in the y direction with respect to y plus the partial derivative of the electric flux density in the z direction with respect to z. Here it gets a little more complicated. We're in cylindrical coordinates. And here's our little differential volume in cylindrical coordinates. And you can see we have dz, we have d rho, and then we have this part here. This would be rho d phi. And by doing some calculations and investigations, it becomes pretty clear after you think about it for a while that the divergence of a vector field in cylindrical coordinates is this expression here. And here we have it in spherical coordinates. And here is our differential volume in spherical coordinates. It gets more complicated. It's still nothing to be afraid of here. You have to think about it for a little while. But this is pretty straightforward if you think about it. The divergence of the vector field would be this expression here. Okay, so now we have the divergence theorem, and this is a big deal. The integral of the normal component, the divergence theorem says that the integral of the normal component of a vector field over a closed surface is equal to the integral of the vector field of the divergence of this vector field throughout the volume enclosed by the closed surface. Okay, what does that mean? That's important. But conceptually, this is not too difficult once you think about it for a little bit. So here's our volume. And if you break up a volume into a whole bunch of little cells, each cell being a differential volume, and if you consider the divergence of each cell, then like you take this little volume right here and you think about the divergence at that location, then that would be like the total flux emanating out of that location divided by the differential volume of that location. Well, the divergence at that location, and if you consider it's the adjacent cells, whatever is coming out of that location, whatever is diverging, whatever flux is diverging out of that location would be converging onto its neighboring cells. And that goes on and on and on until you get to the surface of your volume. So if you break up the volume into this plethora of differential volume cells and consider the divergence of each cells, you get this massive cancellation. And so you're only really dealing with the wall on the outer surface. So in the final analysis, the sum total of the divergence of the flux throughout the volume is simply the net flux emanating through the volume's closed surface. And it's all about what's happening at the surface. In other words, the total electric flux density that's emanating out of the surface, which you find by integrating the electric flux density at the surface over the entire closed surface, is equal to the volume integral of the divergence over the entire volume. So by applying the divergence theorem to Gauss's law, we can express Gauss's law this way: the total electric flux, which can be expressed as the surface integral of the electric flux density integrated over the entire closed surface, is equal to, by the divergence theorem, the integral, the volume integral of the divergence throughout the volume, which is also equal by Gauss's law to the volume integral of the charge density integrated over the entire volume, which is the total charge enclosed. And it's apparent from this, if you see we have this volume integral here and this volume integral here, then del dot D, in other words, the divergence of the D field at any location in space, is going to be equal to the electric flux, the electric charge density at that location. And that is what we call the differential form, or the point form of Gauss's law. So this is the integral form of Gauss's law, and this is the point form or the differential form of Gauss's law. That's all we have. These are the sources that I used to make this presentation. I hope you got something out of this, and we'll see you next time. Have a good one.